All right. Hello, everyone. My name is Randall Fowler, and I will be doing the continuation of this MATLAB workshop. So what we will be going over now is we're going to be going over fast Fourier's transform. So we're going to be looking into the time and frequency domains and how we analyze signals in those domains. So the first thing is when we have our time domain, so there's two things we have when we're analyzing signal in time domain, because we'll have time and then we'll have the amplitude or magnitude or whatever you want to call it. So in this case, what we do is, German might have gone over this already, but we create this is technically a vector, I believe, or an array. We create an array that holds all of the time stamps, basically. So, in this case, we're running it from -2 to 2 seconds. Well, we're going to say we're having a step of 0.02. So if time starts at -2 and ends at 2, then it's stepping at 0.02 every time it goes to a new sample. And it'll have 201 samples. I know I get really confused because most of the things I do start with index at 0. So when you look in MATLAB and the index doesn't really start at 0, it throws you off. Because I look at this and I think, okay, so that means there's 202, but there's actually 201. You can do quick and easy math to figure that out, I think. Yeah, you can do easy math to figure that out. You can take the range, divide it by the steps, and then you just add 1. So in this case, we have 201 samples. If you do the same thing, so if you leave out the steps, it'll automatically assume that we have a whole integer value of 1 that is our steps. So it'll start at 0 and end at 2, and it'll just go from 0, 1, 2. And if you use the same rule, if you do, okay, so our range is from 0 to 2, so our range is 2. Well, 2 divided by 1 is 2. And then you have to add the 1, which that's our 3 points. It's because we include the starting point. That is why we have 3. Because normally, if we didn't include the starting point, so if it started at -1.98, then we wouldn't have to worry about adding a 1. Oh, and I'm not gonna start the presentation like normal just because I don't want to. So we have a sinusoidal function. The top there has a step size of 0.001, and the bottom has a step size of 0.01. So you can see a vast difference between the top and the bottom, because the bottom one, it's very boxy. It's very janky. I don't know what word to use for it. What's happening there is that the step size is 0.01. Well, the frequency is at 10 hertz, which means that if the whole numbers are considered in seconds, at 10 hertz, that means that there should be 10 samples per second. Yeah, I did my math right there. So 10 samples per second. Well, if our step size is 0.01, well, we're running it from 0 to 0.1. So this means that we're only having 10 samples in between. That's fine, but you can see 100 samples is vastly different. And it actually, I think it smooths it out, smooths it out a little bit better than it normally would. So another big thing about this, we're doing this theoretically just in MATLAB, but if we were to take in a signal from like a microcontroller or something, this would be okay. But I would the reason I'm bringing this up is to relate it to the Nyquist theorem, because the Nyquist theorem says that if we have a frequency of 10 hertz for our signal, then we want our Nyquist rate, so our sampling rate, to be at least double that. So, we want at least 20 hertz for our sampling rate. This is believe this is equivalent to 100 hertz for our sampling rate, 0.01. And you can see that's still not great. It looks okay. If it was any lower than that, it would be terrible. But most teachers will say instead of double, you want at least 10 times, and that's what this is. And in this case up here, we have 100 times greater than the maximum frequency, which looks better. My point is that you definitely get a lot more data and you get a lot better values out of that. But if you have to be frugal, then obviously you're going to get something that's a little boxier. Let's go into the next slide here. So taking our signal into the frequency domain, so we already know that our signal should have a frequency of 10 hertz. In the frequency domain, that's all we see is 10 hertz right there. The reason why there's a slope to this is actually because of it's because of how far we let the domain go. In this case, we only let the domain go for one period, but if we were to extend that, this will actually become sharper, and I'll go into the reason why here in a moment. So normally in mathematics, you have to use Fourier's transform or Laplace transform to take things into the frequency domain. But here's the thing: is that's for a continuous function. That's for a continuous signal. What we deal with in MATLAB, we more deal with discrete signals. We deal with things that are going to be like samples, because in our case we don't have 0 to 100 and everything in between. We have 0 to 100 and the steps. So this doesn't take into account that we have gaps in between. If you've learned about Z transform, good for you. That helps. But at the same time, what I'm trying to get into, and I'm going to go to the next slide to get into it, is that fast Fourier's transform, FFT, it is computing Fourier's transform if you have a continuous function, like if you're doing some theoretical calculations in MATLAB. But if you're doing something that's more like what we're doing, which is going to be discrete, it actually doesn't really do regular Fourier's transform. It performs more like a Z transform, except it actually performs in a different method of doing it. They split it up into pairs, and they do a recursive algorithm to calculate all of the data points from time to frequency domain. And it's just FFT. This is right here is our inverse FFT. So you do have an inverse FFT. If you wanted to use regular FFT, you just get rid of the I. Let's see, I didn't really read through this. Yeah, I'm going to continue further. But the reason why I have these are two different algorithms. There's two different processes going right here. I have it written down, the names. I believe it's FIT and DIT. I might be wrong about that, but they're basically different ways that they perform the algorithm performs the math. The reason why we have to have an algorithm like this is because computers aren't finite machines. So if you have a signal that's coming in, or even a discrete signal, we have to be able to split it up so that it can do this much faster. Because if we did Z transform or Fourier's transform more manually, like you would do in a class, it's not very efficient. So this will do it recursively, which will make it a log linear type of function. So analyzing our signal. So if we actually use FFT on that signal above, which is at 10 hertz, what we get is this middle graph, which you can see there's a spike right here, and then there's a spike all the way over here. That's not great. It's because the way the algorithm works is it keeps things only positive. It doesn't show any negative. We're actually supposed to get this negative 10 hertz right here. Negative 10 hertz isn't a real value. There's no such thing as negative frequencies. There shouldn't even be You know, you might think, oh, polarity, oh, direction. No, that doesn't matter. You might interpret it as maybe a reflection, but I think it's just what comes from our algorithm. So how, or I guess let me further go into this. Basically, there's an issue with using FFT. We have to shift it. We have a built-in function for that. It's called FFT shift. What it does is it'll actually take all the data points and it will just shift them. It does not shift the domain. We have to do that manually, which is fine, and I'll show you how. So let me go into how we shift the time domain to frequency domain. Because FFT does that for our amplitude automatically, but it doesn't do it for the domain. So how do we shift it? Well, before we shift it, we actually have to convert it to frequency, the time domain to the frequency domain. And how we do that is there is an inverse relationship between the range and the step size for both. So that means that our step size for our time domain is going to be inversely proportional to the range of the frequency domain. And then the range of the time domain is inversely proportional to the step size of the frequency domain. Hope I said that right, because my brain's everywhere. So you can actually, I think one thing I put right here is you can actually, when you're changing the, the amplitude, the magnitude data, basically you can do it all in one line, and I'll show you. I might not do it in one line just to show you better, but you could do it all at once. But then when you need to shift this is how we convert time to frequency, but then we need to still shift it, and I'll show you how. Basically, what we need to do is we basically need to, subtract it in half, because it goes from 0 to 1,000. Well, it actually needs to go from negative 500 to 500, and it's not too hard. So you could see this. This is kind of all you need, but I'm gonna go through the code and actually write it all up myself. So kind of what I was saying, that the range of the time domain is inversely proportional to the step size of the frequency domain. So when I said earlier that these kind of have a slope to them, or do I still have that other picture that was better? Yeah, you can see that there's definitely a slope right there. Since it's inversely proportional to the range to the step size, that means if we increase the range of our time domain, so that means if we were to go from 0, instead of just one period, if we did several periods, the step size will greatly, it'll get really small. That means that eventually this is going to be, if this is infinitely large, this would just be a delta function that just spikes at 10 hertz. Because the slope isn't actually there. We were here. Is there anything I'm forgetting here? Time. Yeah, I don't know why it's coming up at 50. I think maybe just need to normalize it. I don't remember that being an issue, but we'll go over that. The next slide is on filter design, so I'm gonna actually go ahead and go over to our MATLAB. All right, so first thing we need to do is we need to have our vector or our array of for our time domain. Let's go from 0 to, I'm going to say 2 times pi times, oh gosh, I'm going to pull up something like this. I'm going to say 2 times pi times, no, let's make this easier. Oh, I put an 8, of course. Let's make this easier. Let's put t. T is going to be, let's make this a lot easier. T start, T end, T step. And then we're going to have T start equals T step equals Tn equals, we're going to fill that all in. So if we want 0, 0.001, and I'm going to actually, that might be kind of redundant, but I'm going to symbolize that as our period, and I'm going to symbolize that as like the end of the time. I think it just makes it easier to explain to people or to understand. We're going to do some calculations. So I'm actually going to say the frequency for the signal is equal to 10 hertz. Well, that also means that our omega for that, which we should hopefully all know that conversion, is 2 pi times the frequency, or, well, f signal. So what we do with that is if we, or we're going to put that into our signal, or our sinusoidal function, but another thing we need is we need our period, which is just 1, the inverse of the frequency. So that should be perfect right there. So now we're going to take x is equal to sine of omega times time. And I'm going to take a little further. I'm going to go ahead and figure plot tx axis. We're going to make it, so the x-axis we're going to make go from 0 to, we're going to make it 1 period, 0 to t, or actually let's make it easier, let's make it t end and t start. I like space. T end to t start, and then our y would just be, let's say, from negative, say max of x, and then max of x. So that makes it a bit easier. Make it twice. So then x label, because we're going to label our stuff. Time in seconds. Magnitude, amplitude. Okay. I hope I did nothing wrong here. It's taking a while. Yep, that looks good. And so one thing, don't be deceived, is that I put time is only going from 0 to 1 period. So if I were to scroll to the right here, we're going to see nothing. Ooh, of course, it's loading weird because I think the OBS software is really screwing things up. Yep, nothing. 1 period. So I could change this, the t end. I can make it 5 periods or 10 or 100 periods. So that's all for our time. So now, frequency. All right, so how do we get started with this? Well, or actually, I'm going to start at the same way we started the other one. F start is equal to 0. F step is equal to, we'll get into that in a second. F end is equal to, and then F is equal to, need more space. F start, F step, F end. I hope nobody was thrown off by this. This is easy. There's a max function. It just gets, MATLAB makes it really easy for everybody's life. Okay, so first thing we know is that the range of the frequency domain is the inverse of the step size of the time domain. And then, almost the same thing here, except now we have a little bit of an issue. So I can't just put the inverse of t end, because that's technically not going to work. So, because what's wrong there? What's wrong is that t end, actually that might be fine. Yeah, that would be fine. I could do that. But let's say t start isn't 0, because I'm going to base it off of this could run off of anything. So let's say t start is not 0. Then this would not work. I could do this. I could do t start or t end minus t start. Well, yeah, that works. But I'm going to do something a little fancier. I'm going to do, so I'm going to get the length of t, which if we did from, yeah, okay, so from what we did before, if we did from -2 to 2 with step size of 0.0, what did I do, 0.02? I don't know. But basically, that length isn't actually true. We need to subtract 1 from it. And there's another issue with that, is that that's going to give us, that length function is going to give us how many data points we have. And if we look at the time, we have like 101 data points. In reality, we don't actually, this will give us 101, which isn't correct. We're only going from 0 to, what is this actually? 0 to 0.1. So what we need to do is we need to multiply by the time steps. That should work. If it doesn't, then we'll see. Now, if we think about this from before, it's going to go from 0 to, I don't know, whatever we have it go to. If I were to, here, let's go ahead and do this real quick. Let's plot it, f of t of x. Let's say y is equal to f of t of x. Okay. Let's go ahead, plot. Make it easier in our lives. Because we're using the same code. We don't want to see below, you know, because I'm gonna take the absolute value. So we don't need y to be below 0. I'm gonna do 1.2% or 1.2, so 120%. T start to t end is wrong now, so it needs to be f end. I could make this f start, but the reason I'm not going to, or yeah, I will, sure. I know I'm everywhere. This needs to be enough. This is now frequency. I feel like I spelled that wrong. When you type something in and you think it looks incorrect. Let's see what happens. Let's run it. Okay. Why didn't that come out good? What's wrong? Oh, that's why. And then we run it. I hope it doesn't take forever. Okay, maybe that wasn't why. Why did axis 0 f start to f end? figure plot f, y. Okay, I don't know why I'm having issues. Let's just get rid of it. Why is this not working for me? Am I just being dumb? 0, that's not giving me any issues, right? It's not saying that it can't plot it. F. Oh, F is 0. Why is F 0? Why is that happening? F start is 0. F step is t step length of t minus 1. That should be fine. Semicolons are an issue. Why is it 0? If I run it, it shouldn't make any difference. Oh, I don't know why I put that. Well, found the issue. That should be the issue. Hope it is. Yep, there you go. If you remember, that's what I said would happen, is that we would have everything shifted incorrectly. We have it at 10 here, I believe, right? Put a data point there. Of course not. Okay. Oh, yeah, there we go. It's taking forever. So yeah, so we do have a data point at 10 hertz, but we also have a data point all the way out here that doesn't make any sense. So how we fix that? Well, we know that we're supposed to actually perform FFT shift. I'm actually going to go ahead and throw an absolute value on it, so that would if we ever have any negative values. And then the other thing, so this FFT shift's already going to do it for us. We're not going to have to worry about that. What we do have to worry about, though, is that this is technically incorrect now. So we could take F, and we're just going to subtract it by Fn divided by 2. That should fix all our problems, because if it goes from 0 to 1,000, the center point's incorrect. So we just need to shift it by half of the range, and it should put the origin at 0 for what we want. Okay, so that should be it. Hopefully. If I made anything incorrect. Boom. I think that looks good. I'm going to bring back the axis because I want it. I'm going to, I don't want it to be at T start, or actually I do, or no I don't. I just want it 0 every time because we don't have any negative frequencies. So f end is our entire range. So what we actually want is we want half of the range. And then I want this to be 0. And then right here, actually I'll leave that. I'll change this to y. And I'll change this to 1.2. So another thing I might do, just to keep things simple, so I'm already taking the absolute value. If you want to normalize it, we should just be able to do max of y, and now it will. We might get issues with that here. Absolute value of y. It's kind of redundant, but I don't care. Here, it's bothering me. we'll just do y equals y divided by max of y. So we're taking the largest value, we're dividing it. So this means that everything should be normalized now. And we don't even need this. We could honestly just put 1.2, but I don't care. So I'm going to go ahead and run it. And while it's running, I'm going to go ahead and talk about how we had that slope at that point. We had the slope in the frequency domain. So how do we get rid of this, this slope? Like I said, the range of the time domain is directly proportional or inversely proportional to the step size in the frequency domain. So we're only doing one period. Let's do 10 periods and see what happens. It's a lot thinner. A lot thinner, and if we increased it to 100 periods, it would look like a delta function or a Dirac or whatever. So I will go a little step further. So now if we want, I'm going to add in more signals. So I'm going to add in, okay, actually I could do it right here. So let's say we have a sinusoidal function with, it has a frequency of 10 hertz. Well, let's say we have another one with a frequency of, let's do 2 times pi time, I don't know why I put 8, times, let's put 100 hertz. Is that going to give me issues? Let's put 30. And then, oh, and I need the omega. Oh, not the omega, I need time. Let's carry that over. Let's add in another signal. Let's put 50. So now, if we run this, just for fun, undefined function in. Did I? Oh. MATLAB's so friendly. If you do something wrong, it just kind of tells you what you did wrong most of the time. Okay. We added 2 more signals to just that regular sine wave. So we have our 10 hertz sine wave, which we can kind of see formed right here. And then we have our 30 hertz and our 50 hertz that are added, and it changes and makes things a little interesting. So now, if we take a look over here, you can actually see all 3 signals being represented. If it will pop up. There we go. I think that hopefully worked. Okay, you're just going to have to take my word. 10 hertz, 30 hertz, 50 hertz. There we go. Now it's popping up. But it's still slow. Okay. I think that's it for this video. Any last thoughts? All right. Well, thank you very much for being here. In the next video, I'm going to go ahead and go over filters in MATLAB, and I will also try to touch up on Simulink and even represent circuits in Simulink, which is the extent that I know how to do right now. All right, well, thank you for watching.